Okay, we're live and we're recording. Welcome to the first presentation of the year. Alicia Hou, who's going to talk to us about the monsoon or the precipitation or climate in South America. And why don't you say a few words about you and the topic that you are studying, what you like and how you are related to monsoons.
Okay. So hello everyone. My name is Alicia. I did my PhD at the Heidelberg University, and I studied the South American monsoon for my PhD. So this is my relationship to the monsoon geoseminars. And today I'll be talking to you about some work that I did at the very end of my PhD. So should I get started and share my screen?
Alicia, yeah.
Yeah.
Can you?
Okay.
So what else do you do now?
So now I'm at the National Taiwan University, and now I'm working on reconstructing kind of upper ocean changes in the South China Sea. So a big change in region for me.
Oh yeah, but
yeah.
And the environment. Not really.
Yeah.
Ocean. Ocean.
Yeah, more ocean and very different work location.
Yeah, you must miss Heidelberg. I love that place.
Do you? Yeah, me too. Me too. Very different than Taipei. Much more serene.
Did you walk the Poets hike, the Poets Road on the other side of the city? No, forget it.
I don't know if I did. I mostly hiked at the mountains.
Okay.
Yeah.
Okay,
yeah.
Alicia. I think we have a little problems with the connection, so let's hope that's okay. But please start.
Okay. So I hope everyone can see my screen and can hear me also. Okay, perfect. So today I'll be talking to you, as I mentioned, about something that I did at the very end of my PhD. So essentially the goal for this project was to compile records from all over South America to look at large-scale regional patterns across the continent during the past, to see if essentially if they changed and what mechanisms may have caused these changes in rainfall patterns during past climate intervals. So before I actually talk about the past, I'm going to start by introducing some important things about South American rainfall, starting with some of the major features, and then the seasonal changes in rainfall patterns, and then I'll go a little deeper into kind of the major rainfall dipoles that we see during the austral summer, which is the peak season for the South American monsoon system. So, of course, the South American monsoon system is the dominant rainfall pattern that we see in South America. So this is operating during December, January, February. So this is when the monsoon is at its peak strength, and it affects rainfall in a really large part of tropical and subtropical South America. And a related feature is the South Atlantic convergence zone, which is this elongated band of convective activity that's stretching out of the monsoon domain into eastern and southeastern Brazil, all the way into the subtropical South Atlantic Ocean. We also have the intertropical convergence zone, which mainly affects rainfall more so in northern South America. And we can see that the ITCZ moves north and south, kind of following the zone of warmest SSTs. So during boreal summer and fall, it's further north, and during boreal spring during austral spring and summer, it's further south. And the trade winds, so the northeast trade winds are very important for bringing moisture into the monsoon domain. So it's carrying warm, moist air from the tropical North Atlantic into the monsoon domain. And the southeast trade winds over here, these are important for bringing moisture to kind of eastern and southeastern Brazil, so the coastal regions, and it provides rainfall during the austral winter season. And we also have these extratropical cold fronts. And when they appear during the austral summer, they can they're important for the development of the SACZ, and they also help the southward transport of moisture. The southwesterlies, so these are important for rainfall to the southwestern South America. And the westerlies can also change throughout the year. So during the austral winter, the westerlies are more extended northward, but they're weaker in the core zone, which is around 50 to 55 degrees south. And during the austral summer, the westerlies are more contracted, but they're stronger in the core zone. And BH and NL over here refers to the Bolivian high and the Nordeste low, which are regions of rising and descending air, respectively. And now let's look at kind of the annual rainfall cycle across the continent. So during September, October, November, so austral fall, this is when the monsoon begins to develop. So we see kind of deep convection begins to move southward towards Western Amazonia. And throughout the monsoon development, convection increases over central Brazil and eastern and southeastern Brazil. And during December, January, February, so austral summer, the monsoon reaches its peak intensity, and we have a lot of rainfall occurring over tropical and subtropical South America. And during March, April, May, so this is when the monsoon is decreasing in strength, you see convective activity moving north. And during the season, the ITCZ is also in its more southerly position. So we see kind of increased rainfall in this northern part of South America. And during June, July, August, we see that this is like the dry season for most of the continent. Rainfall is really high in northernmost South America, and this is because the ITCZ is in a more northerly position. It's a bit hard to see here, but southernmost South America is actually also experiencing a lot of rainfall. And this is because the southwesterly winds are more expanded during the season. So now if we look at just December, January, February precipitation, so this is austral summer, so during the peak monsoon phase, we can see that precipitation over the continent, you can see kind of these pronounced rainfall dipoles. So there's one that we see between the monsoon domain and northeastern Brazil. So this is the so-called east-west dipole. And this occurs because when austral summer insolation is increased, you have enhanced monsoon convective activity over the monsoon domain, and you have subsidence and aridification occurring on the eastern side. And we also have this rainfall dipole kind of between the northern hemisphere and the southern hemisphere. And this is essentially because during the austral summer, the ITCZ is further south. So you have drying in this northern area. And we also have a rainfall dipole that's occurring between the South Atlantic Convergence Zone region, which includes eastern and southeastern Brazil and southeastern South America. And this essentially occurs because of changes associated with the SACZ. So when you have perhaps an expansion or intensification or a shift in the location of the SACZ, you have a rainfall dipole occurring between these two regions. But this can also be caused by a change in the flow direction of the low-level jet, which I forgot to talk about in the previous slide. So the low-level jet, so it's kind of coming out of the monsoon domain, and it's bringing moisture towards southeastern South America. So if the flow direction changes, for example, if it flows more north, then you have more rainfall occurring in the SACZ domain. And if it's pointing more southward, then you have more rainfall in the southeastern South America. So this can cause a rainfall change or rainfall difference between these two regions. And of course, we want to know whether these rainfall dipoles existed during the past, especially past climate intervals where we had very different greenhouse gas levels, because this might tell us something about how a change in greenhouse gas concentration might cause spatial rainfall distribution to change in South America. And many studies have looked at this. So typically, these studies have compiled records from South America and compared them to see whether during certain climate intervals, they see anti-phasing in rainfall between different locations. So first, let's look at this study from Meyer et al. 2022. So this study compared records from kind of along the eastern coast of South America here. And so we have kind of these records that are within this red zone that are influenced by the SACZ. And then you have this record here that's from the blue area that's from southeastern South America. And essentially they suggested that a change in during Heinrich Stadio 1, a change in the direction of the low level jet caused rainfall to increase in southeastern South America and decrease in the South Atlantic convergence zone, leading to the development of a rainfall dipole. And then we also have this study from Campos et al. 2022, which looked at whether the east-west dipole was operating during the past at precession timescales. And this study then compiled many records from both the western side of Amazonia and the eastern side, as well as northeastern Brazil. And this is just a subset of the records they compared. And essentially, they're able to show that during the past 1,015 kiloyears approximately, this east-west dipole was in fact operating. But in general, these studies are based on a few records, usually no more, around 10 or so, and they're focused on kind of select regions, for example, Amazonia or the eastern coast of South America. But we do have some studies from South America that kind of take a more continental approach, and they're compiling records from at least throughout the South American monsoon domain. But even so, these studies are still based on relatively few records. For example, this one from Campos et al., I believe is based on around 11 delta 18 records from speleothems, ice cores, and lake sediments. And there's also this study from Deininger et al. And this is based on, I believe, 12 records from various types of proxies within South America. So I think there's still room for studies that want to look at spatial rainfall patterns that are based on more records. And essentially, the goal of this study is then to look at how these spatial rainfall dipoles changed between different time slices. So we wanted to look at essentially 3 different time slices characterized by different background climate conditions. And we also wanted to kind of identify what mechanisms are primarily responsible for the potential change in spatial rainfall distribution when we go from one time slice to another. So now let me just quickly go through the methods that we used for the study. So of course, I started by compiling paleo rainfall records from all over the continent with a temporal resolution of at least 200 years. And after the records were normalized and reinterpolated, I performed principal component and cluster analysis on the records in order to identify kind of the leading modes of spatial rainfall variability. And after this, to assess kind of the spatial configuration of the leading mode of variability, I plotted the clusters onto a map. And finally, I use linear modeling, using the means of each cluster as the response variables and various different climate drivers as predictors. So I looked at things such as insolation, summer insolation, ice volume changes in greenhouse gas levels, et cetera, to in the linear models to understand their influence on the leading rainfall pattern. So these were all the records that we used in the analysis. And as you can see, they're really from all over the continent, and they're based on proxies from all different types of archives. And as I mentioned earlier, I split the analysis into 3 different time slices: the mid to late Holocene, the last deglacial, and the glacial. And so here I've indicated the number of records used for each of the time slices. And essentially the time periods were picked because they, I think, capture the important climate signals during each of these intervals. And they allow me to maximize the number of records that I could use for the analysis for this particular time slice. So now we can finally look at the preliminary results for this study. Let's start with the mid to late Holocene. And if we look at the correlation matrix here, the colors here essentially are showing the between proxy degree of correlation. And the records are sorted according to the results of the hierarchical clustering analysis. So we see one group over here, cluster 1, and these correspond to the pink records here on the map. And we have another group, cluster 2, and these correspond to the blue records here on this map. And I should mention that hope it's noticeable that these records are different sizes, because essentially the size of the dot corresponds to its degree of contribution to the first principal component. So I should also mention that the first principal component reveals essentially the same mode of variability that the cluster analysis does. So I'm using the contribution of each record as kind of like a guide to show how strongly a record belongs to the cluster that it's been assigned to. So these proxy cluster results are plotted on top of austral summer precipitation changes from the mid-Holocene experiment from the AVI ESM model. And we do see a good degree of coherence between the model output and the proxy pattern. We see that the cluster 1 records are primarily from Western Amazonia and the South Atlantic convergence zone region. And we see that the cluster 2 records are from Northern South America, Northeastern South America, kind of southernmost South America. What we can also do is look at the mean of each cluster. So here I'm showing the mean of cluster 1 and the mean of cluster 2. And the cluster means are calculated based on 10,000 Monte Carlo simulations using the calculated cluster mean and the standard error of the mean. And the dashed lines here show the 95% confidence interval. And essentially what we see is that cluster 1 shows that precipitation increased throughout the mid to late Holocene, and cluster 2 essentially shows exactly the opposite pattern. So a long-term decrease in rainfall during this period. And if we then look at the results of our linear modeling, so these are the 3 forcings that gave us significant results. And we can see that insolation seems to explain the highest amount of variability for the cluster means for both cluster 1 and cluster 2. And so here, cluster 1 is plotted against December, January, February, so austral summer insolation. And we can see that the long-term increase in austral summer insolation mirrors the long-term increase in rainfall. And in cluster 2, here I've plotted June, July, August, so boreal summer insolation. We can see that the long-term decrease in boreal summer insolation matches the long-term decrease in rainfall shown by the cluster 2 mean. And what this suggests is that the increase in austral summer insolation caused a strengthening of the South American monsoon system. So we have increased rainfall here and also a strengthening of the rainfall in the SACZ. And as we know, when convection increases in the monsoon domain, we have subsidence and drying over the northeastern South America and eastern Amazonia. So we have drying in this region as well. Because boreal summer insolation decreased during the mid to late Holocene, we see that precipitation decreased in northern South America due to possibly a contraction or southward migration of the ITCZ. But if we look at southwestern South America, based on this study from Lamy et al., the southwesterly winds may have moved or expanded northward throughout the mid to late Holocene. And this may be responsible for kind of the increase in rainfall that we see at site 22. So if the westerly winds gradually increase during this period, we might see a gradual increase in rainfall at this location. But the weakening of rainfall in the southern part of the southwesterly wind belt might be related to a decrease in strength in the core of the wind belt. And this occurs when the wind belt is more expanded. It's weaker in the core zone. And now if we look at the results for the last deglaciation, we see kind of a similar two cluster configuration, but this time the results seem more indicative of a more spatially uniform pattern. We see essentially one cluster here that corresponds to these pink records here, and they're really including all the records from tropical and subtropical South America. And we have another group here that includes these 4 records, 3 of which are from northernmost South America. So you can see that these records are all from north of the equator. And it also includes this one last record from southwestern South America. And again, we can look at the cluster means. So the mean of cluster 1, so the mean of all these records here, is showing a long-term decrease in rainfall. And the mean of cluster 1 is showing a long-term increase in rainfall during the last deglaciation. And if we once again look at the results of our linear modeling, we see that of all the forcings that produce significant results, summer insolation seems to explain the largest amount of variability in the cluster means for both cluster 1 and cluster 2. So over here, austral summer insolation decreased throughout the last deglaciation, and this matches the long-term decrease in rainfall that we see in cluster 1. Boreal summer insolation increased throughout the last deglaciation, and this matches the long-term increase in rainfall that we see in cluster 2. And again, what this suggests is that the decrease in austral summer insolation may have led to a decrease in rainfall in the monsoon domain and the SACZ, which is why we see the long-term decrease in rainfall in these locations. But the notable thing is that we don't see a pronounced east-west precipitation dipole during this interval. And this might suggest that when the monsoon is in a more weakened state, somehow the manifestation of this east-west precipitation dipole is not pronounced. And the long-term decrease in boreal summer insolation seems to be responsible for then the long-term decrease in rainfall north of the equator. So the notable pattern during this interval is a very pronounced interhemispheric rainfall dipole across the equator. Looking at southwestern South America, because we only have 2 records here, it's difficult to make very robust conclusions, but this could perhaps indicate that the deglacial extent of the southwesterly wind belt is located kind of between site 25 and 26, so that these records are located kind of to the north and to the south of the deglacial extent of the southwesterly wind belt. And because the southwesterly wind belt, if this is the case, seems to be then in a more contracted state, then this could explain the increase in rainfall at site 26, because when the southwesterly wind belt is more contracted, it increases in the core zone in strength. And finally, we can look at the results for the last glacial. And interestingly, our analysis seems to have found no significant clusters within the compiled records. And this could be due to a number of reasons. Could be a failure of our analysis, but it could also indicate really there was an increase in spatial heterogeneity during the last glacial. For what reason, or for one reason or another, and that the large spatial rainfall dipoles that we're used to seeing and that we saw during the mid-Holocene and the last glacial seem to have disappeared during the last glacial. And over here, so here I've plotted the 2 clusters based on hierarchical clustering. Even though the results were not significant, I still plotted the results just to kind of see if there's any spatial pattern that can be recognized. And one thing that's obvious is that if you look at the size of the dots for the last glacial time slice, we have a lot of records that do not belong strongly to the cluster that they have been assigned to, which makes sense since our cluster analysis was not significant. And in fact, when I did the PCA on the compiled records, the 2 leading PCs did not explain a high amount of the variability in the proxy records. So essentially both the PCA analysis and the cluster analysis indicate that there were no strong primary modes of variability in the cluster analysis in the compiled records. And it's a little bit difficult to see, but if we do try to look closely, we can see that there are a lot of records kind of with opposite clusterings that are within a close proximity to each other. Here, the cluster results are also plotted on top of the austral summer precipitation changes from the LGM experiment, from the AVI ESM model. And we can pretty much see that there's not a high degree proxy model match based on this comparison. And of course, we want to know why, like if this is actually some sort of signal of higher spatial heterogeneity in rainfall during this interval. And one thing that I did was actually plot the rainfall changes from 2 locations. So we have this one. This is based on a Speleothem Delta 18O record from El Condor Cave. This is from Western Amazonia over here. And this region is sensitive to monsoonal rainfall. And in theory, we would expect rainfall changes to follow changes in austral summer insolation. And we also have this record. It's a lightness record from the site M781235 over here in northern South America. And in theory, we would expect rainfall changes in this region to follow changes in boreal summer insolation. And this is the case when we look at the mid-Holocene and the last glacial, and the last deglaciation. But if we look here, we can see that austral summer insolation changes really don't match rainfall changes at El Condor Cave. In fact, we see almost an antiphase pattern. And it's the same when we look at over here at northern South America. Rainfall changes really do not follow boreal summer insolation, and in fact also seem to be showing perhaps like an opposite behavior. So this might be some hint that the primary insolation forcing that we saw during the mid-Holocene and the last deglacial, which was responsible for producing the large-scale rainfall dipoles that we saw, doesn't seem to be operating as well during the last glacial. And this perhaps is what's causing the high spatial heterogeneity that we saw in the proxy records. But of course, we also want to know why the relationship between insolation and rainfall changes may have changed during the last glacial interval. And one possibility is perhaps a change in greenhouse gas level. So as you can see during the glacial period, greenhouse gas levels were much lower than they were during the mid-Holocene and the last glacial time slices. And I'm thinking it's possible that the change in background greenhouse gas conditions may have somehow altered the relationship between rainfall and insolation forcing. And some support for this idea might come from these model outputs from the Haji EM3 model. So this is the austral summer precipitation from the abrupt quadrupling of CO2 experiment. And this is the austral summer precipitation from the abrupt halving of CO2 experiment. And we can see that when CO2 is quadrupled, we see the development of a somewhat spatially coherent large-scale rainfall dipole between the monsoon domain and kind of this eastern side. So we see more spatially coherent, a more spatially coherent pattern develop. But if we look at the abrupt halving of CO2 experiment, we don't really see this happening. We see, I would suggest, more spatial heterogeneity. There's more patchiness in rainfall response. So this could perhaps be some indicator that a decrease in greenhouse gas levels during the last glacial may be related to the increase in spatial heterogeneity in rainfall distribution during this interval. And so just to summarize what I've been talking about, based on our compilation of rainfall records from all across South America, we see that during the mid to late Holocene and the last deglacial, summer insolation forcing seemed to be the dominant mechanism that generates these large-scale rainfall dipoles that we see in South America. However, during the last glacial, this mechanism seems to not be at play. First of all, we don't see the development of these large-scale rainfall dipoles that we can recognize. And this may be related to kind of an altered relationship between rainfall changes and insolation forcing. And this then may be caused by the reduced greenhouse gas levels during this interval. And of course, this study is ongoing, so there are many next steps to do. One thing is to obviously further investigate what is happening during the last glacial and to test if the hypothesis that we suggest is robust, or using maybe different model outputs, more records, etc. Another really important thing to do is perhaps improve the chronological control of the proxy records that we've used, especially for the records that we use for the last glacial analysis. Because if these records are based on too few age control points, this may be causing the lack of clustering that we see based on our analysis. Another thing that we have to do is reassess the proxy interpretations. So of course, I've only included records that are recording rainfall changes during the past. But as we know, different proxies are associated with various different uncertainties and errors. So I think I should go through each record individually and really assess whether it's providing a true signal of local changes in rainfall amount. And finally, another thing I also need to do is actually compare the results to more models. So I've only shown the comparisons to 2 different models in this presentation. What I really should do is also compare the results to transient model outputs, because of course we're looking at kind of 5 kiloyear time slices instead of just one point in time, one snapshot in time. So it might be more robust to compare our proxy reconstructions to transient model outputs. And that is the end of my presentation. Thank you very much for listening.
Thank you, Alicia. This was fantastically efficient and to the point. I really enjoyed it. Really loved it. Let's open the floor for questions. Don't rush. Cristiano, any questions? Unmute yourself.
Yes. Hello. Hi, Alicia. Congratulations for the talk. Can you hear me?
Yep, I can.
Okay, that's great. Yeah, congratulations again for the talk. Very interesting and timely topic, I have to say. This is a very important contribution. I was wondering about the last glacial lack of clusters that you mentioned, and it's not really a question, this one. Then I have a question. It's a kind of a comment, and I'd like to hear your opinion on this. But this lack of clusters agree with those 2 classic speleoteme records, one from southern Brazil, the Botuverá cave one, and one from western Amazonia, published by the first one by Cruz and Coautors 2005, and the next one is Haisheng 2013, western Amazonia. And they lose this beautiful insolation pacing during let's say the last glacial maximum or marine isotope stage 2, showing that insolation was not anymore controlling the precipitation patterns on those 2 key regions. And so now, with a much more, let's say, continental analysis, with many records, you show that this indeed holds. I think this is very interesting. As far as I follow those works, the authors they say, well, there is this lack of signal, of insolation signal here, but it's too site specific apparently on those papers, and now we see it's not site specific. So I think this is very relevant. I'm not sure if you want to say a few words about this.
No, I agree. I think I need to do more site to site. I need to plot more sites against insolation, perhaps, maybe all the sites that I use for the last glacial, for the last glacial, to really see how their correlation to insolation might be changing during the last glacial, because I think in the presentation I only showed El Condor and the site from northern South America. So perhaps it would also be nice to kind of visualize insolation versus rainfall changes at all the sites to see what is happening in this time slice. And if there's maybe some region that's actually still following insolation somehow, and why that is, if it is the case.
Yeah. And now it's a question regarding the last deglacial. The RV ESM output, you use it to compare the compilation and the cluster analysis too. Is it including a shutdown in the AMOC, or the shutdown in the AMOC is not being simulated by that model?
Oh, that's a good question. I'm actually not sure. I wonder if it would, maybe you think it would be more appropriate to use like a hosing experiment or something that's more so like directly really simulating HS1, or which is really the main, what's really happening during the last deglacial. And that would be a better comparison to the proxy spatial configuration to really see what's going on.
Yeah, this time interval, this time slice, say 18 to 13,000 years before the present that you describe it as deglacial, right? It was strongly impacted by HS1. It's basically HS1 and basically all of the building element put together. And surely that insulation and greenhouse gases changed substantially during this interval, but at least in the tropical domain over South America, the shutdown in AMOC, I mean, played a very strong role. And I wonder if, I'm not sure if this is a run. That was my question of the ESM, if it is simulating this shutdown. Because I would expect to see, at least for tropical and subtropical tropical South America for sure, a very strong role that interhemispheric sea surface temperatures would have over the clusters.
Yeah, so I think actually, now that I'm remembering, I think for the last deglacial, I didn't have a model output to compare to because the PMIP4 models don't have a last deglacial run, I think. But I think you're right, though. It does, at least the clusters do show a really strong interhemispheric pattern, much more so than during even the mid-Holocene. And it's interesting that during this period, we also don't have kind of the east-west dipole. And I wonder if some of these kind of northeastern sites / eastern Brazilian sites are somewhat more impacted by HS1 changes. So I think I remember this perhaps from, I think, Marilia's paper from 2019, where she compiled kind of records from really the north to south along this area to examine HS1 changes.
Yeah. I mean, you're right that there's no model comparison here. I was, fixed to the mid-Holocene and the last glacial. Then I thought, okay, yeah, there should be also a comparison to last deglaciation, because then, you talk about the possible forcings, and but I do believe that a transient run here would help a lot.
Okay.
In order to identify the mechanisms that could be responsible for that. Congratulations, very nice, fantastic work.
Thank you.
Rohan, if you're listening, do you have any questions? It seems he might not be with us. No question. Okay. No question from Rohan. I have bad news and good news. Which do you want?
For me?
Yeah.
Bad news first, I guess.
It's a tough question and a mild question.
Okay.
So for the last glacial,
Mm-hmm.
I don't see any inverse correlation or antiphase. I mean, it's just the start of the deglaciation there. You don't have a correspondent early at 23, or
Yeah, I agree. It's just that if
what I see there is a flat behavior, high oscillations during the last glacial.
True. It's just that during the last glacial, insolation precession is still quite high, so we would expect almost like a perfect match. I would think between
So
the
maybe,
and
yeah.
rainfall. And I plotted the exact same thing for the previous two time slices, and this is for these two sites. And this is really what I see, like insolation really is a perfect match for rainfall changes at these locations. But this time interval, somehow not.
I completely agree, but maybe the forcing then in the glacial is not that. So there's a big discussion on the monsoon in Asia that sea level, basically the glacial boundary conditions are important. So that's a sea level signal to me. So you might consider that. And the other thing, it's a nicer question, not criticizing anything. It's but again, I really enjoyed the talk. I think I understand that the statistical techniques are lumping, but do you have any inkling in them of millennial, like 4.2 event?
I think, I'm not sure if you can see this here, but hard to see this here, but I do remember, so you're talking about the Holocene, of course.
Yeah, they define the Holocene, the sections of the Holocene. I don't know what chronological name those sections are, but by the 4.2 event. So what's happening in the Southern Hemisphere? What's happening in South America?
It's really hard to see here, but when I look at the individual records from the mid-Holocene, I do actually see some records that show this kind of change during this interval. And I was actually wondering also myself what was happening to rainfall during this interval. It's a bit hard to see in the cluster mean, but the individual records, many of them do show this
it's
kind
not
of
fair question because the technique is lumping, but okay.
Yes, but yeah, I saw this pattern and I was also kind of unsure about what was happening there.
Is this published? Are you going to publish it soon?
I hope to keep working on it soon because I've been kind of more focused on my postdoc research and I have kind of put this on the back burner, but it's you know,
it's a very clean study that you should fly with.
Yeah, I hope so. Yeah.
It was a pleasure to meet you and to listen to your talk. So thank you for contributing to the seminar and hope to have you back live to listen to presentations.
Yes, I hope so. New Year resolution.
Yes, and enjoy your vacation.
Thank you very much.
And thank you for everybody coming. Cristiano, nice to meet you.
Thank you, Cristiano.
And Rohan from the darkness. Thank you. And we'll see you to the next seminar.
Yes.
Bye, everybody.
Bye-bye.